Swayam Prabha. Digital India. Educated India.
Good morning. Last class we discussed about, if you recall, it was steady side slip. And how do you define a steady side slip? Suppose the airplane is moving like this, straight like this, then the side slip angle is 0. And if the airplane is instead moving like this, so we have a positive side slip. That is, if I draw a diagram, if I am flying such that relative airspeed is coming from the right, that is, I am moving like this. So relative air is coming from the right. If I see from like this, relative air should come from the right. Okay. So this is the positive side slip angle. And we have seen to execute a positive side slip angle, I need to give aileron deflection, I need to give rudder deflection, and we have seen how their deflections are related. And also we have seen that I can use the steady side slip maneuver to estimate some aerodynamic parameters, especially C and beta, right? And you can do it for estimating few other parameters as well by doing experiments, by using some subset of internal data. The basic philosophy is to, in this course, is to educate you how to conduct experiment, how to think. Now, second part today what we will be doing is basically we will be doing steady coordinated turn. Right. Steady coordinated turn. And that is what today we will be giving you a brief. What is a steady coordinated turn? See, earlier we were discussing about the airplane, let's say in a cruise, it is going like, level cruise is going like this. Right? For a steady side slip, airplane is going like this. But for a coordinated turn, steady coordinated turn, I am turning like this. And that I can do if I have some bank and I am using some rudder deflection. I can as well do it like this, just give me rudder deflection. But the problem is, as I give rudder deflection, you could see this left wing will see a larger velocity because of this turn, so there will be more lifts, so it will try to bank. So you use both rudder as well as aileron. And you turn it like this so that beta is 0 all the time. That is very important. In a steady coordinated turn, beta is 0, and of course, you ensure that you are not losing the altitude. Right? If that is agreed that I am executing a maneuver using aileron and rudder and some throttle setting such that I am turning such that beta equal to 0, then how the Sixdorf equation will get modified, the first thing we will see. Right? Because when you will be doing experiment and we will be putting the data, I should know what is the mathematical model I am going to use, which will be a subset of a Sixdorf equations of motion. Right? So let me take up that. For a steady turn, let's say the Fy equation from Sixdorf, you are aware it is half rho V square S into Cy P into Pv by 2 V plus Cy R into Rb by 2V plus Cy beta into beta Cy delta A into delta A, Cy delta R into delta R. This is the aerodynamic force which are coming because of general in the Sixdorf. If there is a roll, if there is a yaw rate, if there is a beta, if there is a aileron deflection, if there is a rudder deflection. Of course, the Fy will have some component because of the bank, which will be the component of the weight, right? And that term is plus mg, general term is mg cos theta sin phi. So this is the thing new I have written. This is part of the one of the equations of a 6-DOF model. You should understand before you do an experiment that this part is aerodynamic force and this part is because of the gravity, and theta is the pitch angle. Okay. Now the question is, we are talking about steady coordinated turn. I like to investigate which of these terms will contribute for a steady coordinated turn. What is CYP? Let us understand. What is CYP? It is the side force. Let's say if I take the axis system, which conventionally follow, this is X, this is Y, and this is Z. So if I use this as, if I assume this is an aircraft, then if I am moving in this direction, you know X-axis is this, Y-axis is towards you, and Z is downward, right? X, Y, Z, right-hand system. Now what is beta positive? Beta positive is if the wind is coming from the right. So this is the beta positive direction. And if the wind is coming from the right and there is a vertical tail, which way the vertical tail will experience a force? It will be in the opposite of Y direction. Is it clear? If I see it like this is X, this is Y, and this is Z, and positive beta wind coming from here, and this is the vertical tail. So vertical tail will experience force towards me, and this direction is opposite to positive Y direction. Okay, so for a positive beta, Cy, which is a non-dimensional coefficient of Fy, will be negative. That is, I will say Cy beta will be negative value. Right? Okay. And by diagram wise, if I write, this is my fuselage, this is the tail, this is the wing. If this is positive beta, let me draw an arrow. If this is positive beta, I know by convention this is X, this is Y, and Z is inside the board. For positive beta, this vertical tail which is here, it will also see closer to positive beta. So there will be a force in this direction. And this direction is opposite to the positive Y direction. So this Fy, because of beta, is negative, or we say dCy by d beta is negative. This is dCy by d beta, which says per unit beta, how much Cy will change direction wise, that is negative. We understand this, right? Now let us talk about CYP. What is CYP? CYP is, suppose this is the airplane. What is P positive? P positive is right wing going down. That is the right wing going down is P positive. So if I roll this airplane positive like this, now imagine there is a vertical tail here. So as it rotates, the vertical tail also rotates in same direction. So it pushes the air towards positive Y. So it also experiences a force in the negative Y direction. Is it clear? Should I repeat again? Let us assume I am repeating this for your clarity. Let's say this is the vertical tail, small the vertical tail. As I am giving positive P, right wing going down, this tail is pushing the air. So there will be a reaction on the tail in this direction, and this direction of force is opposite to the direction of positive Y. So Cy because of P also will be negative, as the major contributor is the vertical tail. So I will say C also negative. Sometimes this sign may changes because of sweep back of the wing, because of high wing aircraft, because of the fuselage. But I am giving you a general idea how to find the component. When I write CYP negative, I am actually meaning this contribution is primarily because of vertical tail, right? So in a normal aircraft, you may find because of sweep or because of fuselage effect, this sign may not be what I am telling, or numbers may not be what I am telling. Similarly, CYR, if you see what is CYR, and if you recall in our earlier class, R means your yaw rate, that is, yaw rate is positive, with right wing going like this. This is yaw rate positive. And imagine this airplane is taking a yaw rate about center of gravity. It is turning like this. So again, this tail is pushing the air this direction, so it will experience a force in this direction. And incidentally now, for a positive yaw rate, the force experienced by vertical tail is in the positive y direction. So CYR, because of vertical tail, if it is predominant, which is generally true, will be positive. Right? Now I come to CY delta R. For time being, I neglect this. I say this is not much. So if I talk about CY delta R, let us see what is the sign of CY delta R. Again, I come here, delta R means rudder. This is the rudder, let's say, if I deflect it towards left, which is the positive rudder deflection. I repeat, towards left, when I look from the top, is a positive rudder deflection by convention. So if I am deflecting towards left and moving forward, then the force will come in this direction, which is in the positive direction. So CY delta R will be, this sign will be positive. This much understanding you need to have when you are doing experiments. At least signs you should know from the first principle. That is why I thought I will explain you this. Then we come back to our experiment. So this is the expression of Fy, which are essentially I have written the forces. And the kinematics part, if I now want to equate, if you see the Sixdorf equation, this term, whole of this term will be equated to m v dot plus Ru minus P W. So V dot is the component of V along total V, which is half rho V square, capital V square, component that V along the local y direction. And U is the component of total V along x direction, local x direction, and local z direction is W. That is, aircraft, if it is moving like this, and then suppose this is the relative air speed, it has a component along x, along y, along z, and same aircraft if moving like this, and let's say velocity is still in the x direction, in the parallel to the ground, then the component will change. So that is why I am saying, which you know that VW, UVW are the component of total velocity along local body axis x, y, z direction, right? And V dot is, of course, you understand, is the rate, is the acceleration along that direction. Okay, this is the part which I am taking out from the Sixdorf equation of motion, which you have already done in one of our courses, and you are aware of it. Now I put some assumption. I am assuming that theta is 0. That means what? I am conducting the experiment so that the pitch angle is very small. Okay? Pitch attitude angle, please under this theta, right? Very small. That is why I am taking it 0. And also I am assuming that the bank angle is also very small, maybe within 10 degrees. If I do this, so bank angle phi less than or equal to 10 to 15 degrees, I say 10 degrees when I do the experiment. Once I do this, I make an approximation that this term mg cos theta sin phi, I can now easily write it to be mg phi. No objection, right? Now, once I am doing a steady coordinated turn, that means I know that there is no beta. So this gentleman goes for steady coordinated turn. Because in a steady coordinated turn, I am turning like this. So every time beta is 0. The attitude is aligned towards the velocity vector. Okay? Similarly, when I am doing steady coordinated turn, what is the value of P? It is not doing anything like that. It is only turning like this. So P is also 0. So I drop this term because of steady coordinated turn approximation. What about R? Can I drop it? You cannot drop because R is there, it is turning like this, right? So this stays, and then delta R is there, this also stays, and we have taken an approximation that Cy delta is weak, so I am not adding that into the equation. So finally what happens, if I do these assumptions, then my equation becomes mg phi plus half rho v square s into Cy r into Rb by 2v plus Cy delta r into delta r. This is equal to m. Now, v dot, it is a steady coordinated turn, so v dot automatically goes. There is no role p, so this pw, so this goes because steady coordinated turn, there is no role, so this also goes. So what is remaining now is m u into r, right? And you could easily understand when I am doing a steady coordinate turn like this, and I will not be very much incorrect if I write v equal to u as I am moving like this. Every time aligned to the velocity vector x-axis aligned, so I can replace this u by v. So I can write mg phi plus half rho v square s into Cy r into Rb by 2v plus Cy delta r into delta r equal to mvr, where r notation wise I am using this, so let me, r is the yaw rate. Now see, what is this mvr? mv, r is angular rate, mv omega, it is like mv square upon r, like centripetal acceleration. Okay? Anyway, it's true. If the airplane is turning like this, it is like a stone being turned by a string. So some force must be making it happen to give a centripetal acceleration in the circular path. So that is the effect mvr, which is the centripetal acceleration. Who is causing it? For a stone, I am rotating a stone with a string. The tension in the string causes that. So somebody must be causing this acceleration. Who is causing it? Primarily mg phi, component of the weight, and aerodynamic force this. This physics clear, right? So now what we will do, we will do further little approximation. Engineers are always infamous for doing approximations, and many a times or sometimes something very realistic comes out. So if I do an approximation, less this aerodynamic force contribution is negligible. Anyway, you could see that rudders are designed to give moments. That's why there is a large momentum, not force. Force is from the wing side. So this is a force component from the rudder, and this is a, because of cross, because of rate, there is a side forces coming. So we can, not a bad idea to see what happens if I say, gentlemen, this force component is not very appreciable compared to the force coming because of the weight component, which is at a bank angle of phi. So if I neglect this, then what I get is minus, I'm getting is, sorry, right, mg phi is equal to mvr, or r, whatever notation I am writing, or I can write gets cancelled, so I am writing it as minus Vr plus g phi equal to 0, or you could see g equal to Vr by phi. So how do I use this information and get some enrichment through experiment? What I will be doing, I will actually go for a steady coordinated turn. I will take stopwatch. I will tell the pilot, take a turn of 90 degree or 180 degree, depending upon mutual agreement. I will have a stopwatch, and I will know how much time it has taken to turn. So from there, I will get the value of r. That will be how the total angle turn divided by total time. So I know R, V I know from airspeed indicator, phi I know from the turn bank indicator. So I will measure, acquire those data and find this ratio. And if it comes near between 9.7 to 9.8, something like that, and which should remain constant fairly for that altitude. So you know that, yes, this ratio has to be closer to the value of G. So then you are getting understanding whatever 6th equation you have understood, you have applied it correctly and your assumptions are realistic. If this value goes off, then the assumptions are wrong. For example, if you are banking at a 60 degree and you are having some positive theta values and your rudder is very, very powerful, then you need to be careful that the value of G will not come. That means your experiment you are designing is not correct, because the G equal to VR by phi will only come when theta equal to 0 and phi is very small. Right? And this indirectly also tells you how good is your 6th model. Right? So this will be also one of the experiments. And this is a theory I am building it up. Then we will be going for a session. We will actually demonstrate how to do these experiments. Clear? But do not forget, for a steady coordinate turn, you are supposed to measure yaw rate. That is, you have to tell the pilot, I want to take a turn at 90 degree or 180 degrees. You should have a stopwatch. As he starts taking a turn, ensure that he is doing a coordinated turn, no loss of altitude, the speed should remain same. And in this, with the stopwatch, you find what is the value of R, yaw rate, use turn bank indicator information to get phi, use airspeed indicators to get the value of V, and offline you see this ratio, whether it's coming closer to G or not. If it's coming closer to G, the assumptions are fine, because you've assumed the equation of motions to be perfect, right? Okay. Now, so this is one part for this experiment. Now let us see what more information we could get out of this experiment. Let us watch out for rolling moment coefficient. In a rolling moment coefficient, I can again write like CLP, expand like CLP by PB by 2V plus CLR into RB by 2V plus CL beta into beta plus CL delta A into delta A plus CL delta R into delta R. Right? So when the airplane is doing, or the pilot is executing a steady coordinated turn like this, what is the value of CL? CL has to be 0. If there is a positive value of CL, it will turn like this or turn like this. Since it is just making a coordinated turn, so CL is, no rolling moment is there. So CL is 0. So it must satisfy CL equal to 0. So when I put this 0 equal to CLP into PB by 2V, and I ask myself a question whether this contribution of rolling moment will be there or not, I immediately see that when I am doing steady coordinated turn, there is no P, there is no roll rate, so this gentleman goes off. And plus CLR, similar story with CLR, if I say, will you be correct? No, because there is a R. When I am taking a steady coordinated turn, there is a yaw rate. So I cannot drop this. So this stays. What about CL beta into beta for a steady coordinated turn? What is the value of beta? We have seen beta is 0. So this man also goes. Then of course CL delta A, which is coming from aileron, and plus CL delta R. CL delta R means when I deflect the rudder, if I deflect the rudder like this, it gives a yawing moment, plus there is a force in this direction that will give a rolling moment also. That is why you have CL delta R. So if this is true, then what do? I write simplified equation 0 equal to CLR into RB by 2V plus CL delta A into delta A plus CL delta R into delta R. We will be doing further approximation. We'll see if you study between these two terms, CL delta A and into delta A, CL delta R into delta R. Which control surface is primarily responsible for giving rolling moment? By design, it is the aileron. From rudder, it comes as a second effect, because rudders are used for directional motion, for turning the airplane. However, we should also remember that during stall, rudder is our best friend. But in general design, when you are not going to stall and all, the primary rolling moment comes from the aileron, and that is designed for. Aileron is for rolling motion. So I again do an approximation as an engineer. I said, between these two terms, this contribution is predominant. So I say, thank you very much. You also go. So now you have 0 equal to CLR into RB by 2V plus CL delta A into delta A. Do not forget to bring this equation, what are the assumptions we have made. And also you know that from the earlier equation, you have seen R equal to G phi by V. Okay. Then if I now substitute this R here, what will happen? Then it will show that CLR into R is G phi by V into B by 2V, because I am replacing the expression for R by this. This expression of R came, remember, for the steady coordinated turn under those assumptions. So I am simply, in this equation, I am substituting the expression for R, this plus CL delta A into delta A equal to 0. So CLR into R is this, into CLR into RB by 2V. So this is fine. Now what I do, if I do some manipulation, I could show that, let me write CLR into G phi by V into B by 2V, yes, same expression, plus CL delta A into delta A equal to 0. So I can write CLR into G phi by 2 into B by V square, V have taken here, 2 have taken inside the bracket, is equal to minus CL delta A into delta A. No issues? This is the expression you understand. Now, here from here to here, nothing great we have done. The 2 I have taken inside this G phi by 2, this V has gone outside, so V square, and this is this. So you could easily see that delta A by phi varies with 1 by V square. This is very extremely important observation. Delta A by phi varies with 1 by V square. What is the meaning of this? As you are going to make a bank angle change using an aileron, you will find that as I increase the speed, the ratio will go on decreasing, right? It goes inversely. So this easily you can check from your experimental result, because you know you have the data available, which is aileron deflection, you have phi through turn bank indicator, you have V from airspeed indicator. And where from this expression has come? It has come from a 6DOF, and we go on adding those simplifications, right? And if you get something closer to this, you will understand, oh, my 6DOF, my understanding is correct, my assumptions are correct, are meaningful, which will help you in understanding the equations of motion. This expression is extremely important, and this will tell you how to design, when you are designing the controller for an airplane, to make the pilot have a good handling qualities. You should be very, very careful that delta A by phi will go inversely with V square. Okay? That's extremely important. Okay, thank you very much.